we're going to continue in this chapter and look at how we find the volume of a solid of revolution. There's two ways to do this. In this section, we're going to look at what we call the disk method. So first, we are limiting ourselves a little bit. The types of solids are solids of revolution. So you take a region, just like a region we might have found the area of in the last section. But rather than find the area, we're going to take that whole region and revolve it about some axis. Often it'll be about the x-axis or a y-axis, but what we set up here will be valid for any horizontal or vertical line. So we're going to look at the disk method for doing this today, and we're going to start out looking at this sort of generic setup here. So in this sketch, the function, that we're looking at is this top curve right here. There's our function. And we're taking a look in particular at the region underneath the function, so between the function and the y-axis, and the x-axis. So we have this shaded region here. I kind of shaded it in the original sketch, but that's the region. We could find the area, and if we wanted to find the area of that, what we would do is draw a rectangle just like the one that's here, right? I'm going to just outline it in red. We draw a rectangle like this that has a delta x width. Now, in this sort of simplified sketch, the height is just the y-coordinate because the lower bound is the x-axis, whatever that length is, right? So it has a length, and the width is delta x. Now, because we want to find the volume, because we're working with a solid of revolution, the actual solid is what we get when we revolve this whole region, the shaded region, about the x-axis. So there's our axis of revolution. And we get this kind of horn-shaped region here, this horn-shaped solid. And to get the volume of that solid, we're going to take that sample rectangle that we drew, and rather than find the area, we're going to revolve that rectangle about this axis. And if you revolve just this one rectangle about the axis, you get a disk shape, right? So let's take that disk. Let's imagine that we could just pull that disk out. I'm going to bring it over here, and that's what I've sketched over here. I basically pulled that disk out and then flipped it, over. And when we do that, we could see that it's really kind of a short and squat cylinder. So the radius of this cylinder comes directly from the height of that, or the length of that rectangle. The height of the cylinder comes from the width of the rectangle. And we know how to find the volume of a cylinder. You might need maybe you remember the formula, maybe you don't. You'll know it really well by the time you've done this section and done some practice. But for a cylinder, the geometry formula, to find the volume of a cylinder is V equals pi r squared h. Now, if we scroll down, you're going to see that we introduce some integration formulas. I do not bother memorizing these formulas ever. I know that if I want to evaluate a volume using the disk method, this formula is really the only one that I need. As long as I can connect the radius of the cylinder and the height of the cylinder to the sample disk, then just like with the area under a curve, finding the volume of that sample disk, the integral will write itself. So the radius of this disk is y, or f of x. So f of x and then squared, because I have to square the radius, times the height. The height in this case is delta x. Now here we're kind of going over the setup as if we had to draw a vertical rectangle. Sometimes there will be scenarios where you have to use a horizontal rectangle and you have a delta y, and in those cases, pi r squared h still works, right? And we still can just sort of connect those, the radius and the height to the actual disk that we come up with when we draw a sample rectangle. So this is what the volume of this sample disk is, and that means that the volume of the whole solid is the integral of pi f of x squared dx. Delta x turns into dx, and then we need limits. So the limits of the integral come from the limits of the original region. So again, like if I were actually finding the area of that region, what would those limits be? And those limits are inherited to the integral for the volume. And in this case, in this sort of generic case, looking over here, I'm highlighting them in yellow now, we're integrating from a to b. And usually, I like to pull constant factors out of an integral, so I'm going to just pull the pi outside. So there's sort of the generic setup. Now down here, in this generic setup, I just have the function f of x, because that function f of x, the lower bound was x equals 0. Here's a more general statement of what that integral looks like, where we just call it r of x, because depending on what your bounds are, it might not just be the single function that is your radius. So always sketch, just like with areas, always sketch, know what your region looks like, draw that sample rectangle so that you know what your sample disk looks like. And if you can find the volume of your sample disk, then the integral will write itself. So let's do an example. We're going to find the volume of the solid formed by revolving the region, bounded by the graph of f of x equals the square root of 3x minus x squared, and the x-axis, and then they tell us between 0 and 3, so they give us some bounds here, about the x-axis. So I'm going to do a couple of things. They provided the sketch for us, which is nice of them, and if they hadn't, we could sketch it ourselves, maybe use the calculator to help us. So it says it's being revolved about the x-axis, so I'm just going to kind of indicate that on my sketch, and then I'm going to outline the region, so it's bounded by this curve and the x-axis. So that's important to know the bottom curve. Now, with when you end up with disks, the axis of revolution is abutting the region itself, right? So it's like kind of part of the boundary. If the axis of revolution is kind of separated a bit from the region, we can still use a modified disk method. We call that the washer method, and we're going to look at that in a little bit in this same section. So we're revolving about the x-axis. Now, when you use disks, here's the great thing. They don't tell us to use the disk method, but of course this example is in this section on the disk method, so we're gonna. But sometimes you might be working on a problem and you know that you want to find a volume, but you're not sure whether you need to use horizontal or vertical rectangles. And I'll just note that with the disk method, you have to draw the sample rectangle so that it is perpendicular to the axis of revolution. So, it might have been kind of clear when we looked at this region that we should use vertical rectangles, just because with vertical rectangles the upper and lower bounds remain consistent throughout the region. But we can further see that we need to use vertical rectangles if we're going to end up with a disk. if I use horizontal rectangles, we'd end up with a different shape, and we call that a shell, and we're going to look at that in the next section. So there's our vertical rectangle. A vertical rectangle has a delta x width. And if we were to revolve this rectangle about the axis, it would kind of look like this. Right, so there's our disk. I can kind of sketch it again up here. I like to draw them so it looks more like the cylinder with a circular base as opposed to a cylinder on its side. I don't know why. I think it just makes it easier for me to pick out, you know, the dimensions, the radius and height that I need. But the radius here, is given by this length of that rectangle, and that top minus bottom is the function f of x minus 0. So the radius is the square root, is our function, square root of 3x minus x squared. Our height here is delta x. That comes from the width of the rectangle. So the delta V, the volume of this sample disk, is pi r squared h. I always start by writing that down. Pi r squared h. So this is pi times, I've got the square root of 3x minus x squared squared, I have to square the radius, times h, which is delta x. So that is pi times, of course if you square the square root, those will cancel. We get pi times 3x minus x squared delta x. There is our delta V. Since we have the volume of our sample disk, really the integral falls right out of this. So I'm going to pull the factor of pi outside. Pi times the integral 3x minus x squared dx. And our limits, they pretty much gave them to us right at the beginning. They told us that we were only considering this function from 0 to 3. And now we can integrate. This, we are done the hard part, right? This is the hard part. Visualizing, setting up this integral, finding the volume of the sample disk, and then writing out the integral that models this problem. That's the hard part. Now we can integrate. And the integration is a little easier because, again, like we saw with the areas, a lot of these are that we end up with are polynomials. That's not always the case. Sometimes you need to use a U substitution. Sometimes there'll be different kinds of integrals, but a lot of these problems that we run into here are going to be polynomials. So integrating, we get 3/2 x squared minus 1/3 x cubed. And we're going from 0 to 3. We're going to plug in our limits. So our upper limit is 3/2 3 squared minus 1/3 3 cubed. And then every term has a factor of x. So when I plug in 0 for x, the whole thing zeroes out. If you use your calculator, or you could do some good old-fashioned arithmetic, that's always enjoyable. But if you use your calculator on this part here, you get 9/2. So it's common to write that instead of pi times 9/2, to write it as just 9 pi over 2, like a single fraction is usually how we write it. And almost always, unless that it's an applied problem where there are maybe some understood units being used, or I could see what I'm measuring, or there's something, that I'm actually measuring as opposed to kind of this abstract three-dimensional solid of revolution, almost always just leave it in terms of pi. And you'll see that as you do the practice exercises and you check your answers in the back of the book or on CalcChat, they're going to almost always write them in terms of pi as well. There are some actual application problems where we're going to have some units applied to them, and a lot of the time then we'll approximate to get a sense for like the magnitude of our value. Let's do another one here. Here they've provided the figure again. We want the volume of a solid formed by revolving the region bounded by, okay, f of x equals 2 minus x squared. That's the parabola opening downward. And g of x equals 1. That's the horizontal line they drew. About the line y equals 1. Okay, so here's our region. There's our region. It's no longer abutting the x-axis, but it is still abutting the axis of revolution because they've changed, they've set the axis of revolution to be the line y equals 1, and that is our function g of x. So I know I got to draw my rectangles so that they are perpendicular to the axis of revolution. That's got to have a delta x width, which will end up being the height of our cylinder, our disc. And if I revolve this, there's our disc. There's our sample disc. So the radius is the height of the disc. The radius of the disc is the height of that, length of that rectangle, I guess I should say. So the length of that rectangle is a top minus bottom length, and that is 2 minus x squared minus 1, or just 1 minus x squared. That's our radius. So that means that our delta V, volume of the sample disk, pi r squared h, that's pi times 1 minus x squared squared. The height of the cylinder is the width of the rectangle. That's delta x. Now I know that we're going to be integrating this. So when I think about approaches to integrating something that looks like 1 minus x squared, what we're going to do is just FOIL that out so we have a nice polynomial that's expanded. I'm going to do that right now in this expression. So 1 minus 2x squared plus x to the 4th, delta x. So there's our volume of the sample disk, and that means the volume of the solid of revolution, the whole thing, is pi times the integral of 1 minus 2x squared plus x to the 4th. The only thing that we're missing are the limits, and those limits are going to come from these points where the two curves intersect, or where the parabola intersects with the line. It's a dx integral, so we want the x coordinates of those points, and we're going to find them like we usually do by setting these curves equal to each other. So 1 equals 2 minus x squared. That means that 0 equals, let's see, 1 minus x squared. And we can actually, we can factor this. 1 minus x, 1 plus x, and we get x equals 1, x equals negative 1. So we're going to integrate from minus 1 to 1. And again, now this is the hard part. This is the part, this is like the new stuff we're kind of learning. We did do some of it in Calc 1, so maybe it's a bit familiar, but this is the hard part of the work. And now we can evaluate this integral. Let's integrate. It's a polynomial. We love integrating polynomials because they're pretty easy. The integral of 1 is x minus, using the power rule, we got 2/3 x cubed plus 1/5 x to the 5th, evaluating from minus 1 to 1. Let's see, I'm going to actually give myself a little space here. Plugging in 1, we get 1 minus 2/3 plus 1/5 minus, and if I plug in -1, we get -1 minus 2/3 times -1 cubed plus 1/5 times -1 to the 5th. Be careful with your signs. It's easy to make sign errors here. Let's see, 1 minus 2/3 plus 1/5. Convert that to a fraction. 8/15 for the first one, and then for the second one, let's see, I'm just going to simplify with the signs first. -1. -1 cubed is a -1, so that's going to turn into a plus 2/3 because that's a subtraction. And then -1 to the 5th is -1, so that's a minus 1/5. So we know we have 8/15 minus -1 plus 2/3 minus 1/5. And that's a negative 8/15. We're subtracting it, so really we're adding 8/15. So that's 16/15. So this overall we get 16 pi over 15. Okay. So we saw that when the region that we're revolving about the axis, when the axis of revolution is abutting the region itself, we get these nice solid disks. But if the axis of revolution is sort of maybe not completely up against the region, there's some space, in between the region and the axis we're revolving it about, then when you take that rectangle, that sample rectangle, and you revolve it about the axis, you end up not with a solid disk, but with this disk that's like got a hole punched in it, and we call that a washer. So the way that we model that, if you have a disk with a hole punched in it, I'm just going to kind of sketch this out in the top margin here. So there's a solid disk, and then if I have a hole punched out, I don't know if I've drawn that very well, but we've got this little hole punched out in that disk. So the way that we find the volume of this washer is I take the volume of the whole disk, right? Like, so here's the center, right? And from the center out, that's the big radius, so I'm going to call that capital R. So I could find the volume of that, like imagine there's no hole punched out at all. It's a solid, the full solid disk. That's a pi big R squared delta x. Now the hole has the same delta x, right? That's the same, but it does have a different radius. I'm going to call that little r. And so if I'm punching out that hole, I'm just going to subtract out that disk that we kind of get from the hole itself. And so that looks like this down here now, this delta V equation. I've got the big disk minus the hole. That's basically what this what that expression is. This is the big disk minus the hole, which is really a small disk. Whoops. And both of these terms have common factors of pi and delta x, so if you factor that out, it just looks like this. And so that gives us this, volume, this integral formula for the volume using the washer method. But again, I don't really memorize that formula. I just think about putting this piece together. And then again, if I can write an expression for the volume of the sample washer, the integral will write itself. So I don't worry about memorizing an integral formula. I kind of just try to think of the piece that I need. So we're going to do an example here. We want to find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. Now they don't say this explicitly, but this is really just in the first quadrant. Y equals the square root of x doesn't exist in any other quadrants. So when I sketch this, let's see, when I sketch this, I'm going to get kind of a nice biggish picture. Oops. So there's the origin. So the square root of x and x squared, if you could throw it in the calculator first, you might have to adjust your window. In fact, if we look at that here, y equals square root of x, y equals x squared. And if I look at this on the standard window, from -10 to 10, you could see it's really just sort of a small section, right? And you can zoom in. One nice zoom feature is the zoom box. You could just kind of draw a box. So you locate the corner of one box, you hit enter, and then kind of like an Etch-a-Sketch, you move the second, you draw the box by using the arrow keys to just locate the other corner. And so we can see they actually intersect. This will not be surprising once we see it and state it. They intersect at 1, 1, right? Clearly, you could see, algebraically, if you solve this, they both have to go through the point 1, 1. So here's 1, here's 1. The square root of x is the one that bends up like this, and x squared has this opposite curvature to it. So there's the region, and we're revolving it about the x-axis. So clearly the x-axis, the axis of symmetry is not like abutting the region, right? The x-axis is not one of the boundaries of this region because both boundaries are curved. To end up with washers, just like with disks, we have to draw rectangles that are perpendicular to the axis of revolution. So I'm going to draw this vertical rectangle, and I can just get, quickly confirm that vertical rectangles are good for us here because as I move that rectangle left and right through the region, it's always the square root function on top and always the parabola, the x squared function on the bottom. Now, what's really important, I'm going to just, if you're listening to this, if you're watching the video, just stop writing for a second and listen. And what I'm going to say is really important because it's a common mistake. When we're using washers, we don't actually use the length of that rectangle itself in the integral. I'm going to say that again. We don't actually use the length of the rectangle itself in the integral. What we do is we put together, what if I were just revolving the top curve, right, about this axis, and I get that's my big radius. So big R is the square root of x. And what if I were just revolving the x squared curve, the bottom curve, about the axis? And that distance from the axis up to that bottom curve, that's our little r. So, and let's see, I'm just going to put a little detail here. This point is 1, 1. Okay. So now, our sample washer, the volume of a sample washer, this looks like pi big R squared delta x minus pi little r squared delta x. And I can factor out the pi and the delta x, so I get pi times big R squared minus little r squared delta x. So again, I'm not using the length of that rectangle when I set up this volume of the sample washer. What I need is to get big R squared minus little r squared and just simplify that expression. So big R squared is the square root of x squared minus little r squared, oops, that's x squared delta x. Simplifying this, we get x minus x to the fourth. Okay. Now that we have written we found an expression for the volume of the sample washer, the integral is just going to fall right out of this. The volume that we want is pi times the integral x minus x to the fourth dx. And now the limits, if you just consider the region, you could show this algebraically, but it's fairly clear. They both have the point 0, 0. They both have the point 1, 1. So the x coordinates, it's a dx integral, so we need x limits. Those are 0 and 1. And now we're almost done. Integrating this function, we get 1/2 x squared minus 1/5 x to the fifth from 0 to 1. So let's see, plugging in 1, we get 1/2 minus a fifth minus, if you plug in 0, both those terms have a factor of x, so the whole thing zeroes out. 1/2 minus 1/5 is 3/10. So 3 pi over 10. All right. Let's try one more. All right, so this last example, as the introduction says, we're going to end up integrating with respect to y. I think we'll be able to see why we need to do that after we sketch it. And a vertical axis of revolution. So we want to find the volume of the solid form by revolving the graphs bounded by these equations. Our first equation is y equals x squared plus 1. All right, so x squared plus 1. I'm going to kind of zoom in. This is mostly in the first quadrant because we see that it's bounded by y equals 0, x equals 0, and x equals 1. So our curve is x squared plus 1. So that's a parabola that opens upward, that starts with, has its vertex at 0, 1. And the line y equals 0, so that's the x-axis, x equals 0, and x equals 1. X equals 0, x equals 1. All right, so our region looks like this. We're revolving at about the y-axis. Look, if we're revolving this about the y-axis and we're going to end up with either discs or washers, we have no choice but to use horizontal rectangles. So look, when we first sketched this, it looks like, I wouldn't blame you for thinking, why don't we just use vertical rectangles? Because, the boundaries are consistent, right? It's always the parabola on top and always the x-axis on the bottom. But if we're going to end up with a disc or a washer, we've got to use horizontal rectangles. Now that gives us a bit of an issue because a rectangle drawn down here, right, has the right x is always 1 and the left x is 0. But once I switch to drawing the rectangle up here, now the boundaries change. And we've been really clear about how that's kind of an issue that we like to avoid. However, we don't yet have the skills to do a shell method. That would be the other kind of technique that we could use. But we can make horizontal rectangles work for us here. And what we're going to do, I'm going to draw a little boundary, a little kind of border. We just have to deal with what's below the dotted line separately from what's above the dotted line. So what's below the dotted line, we could deal with that actually really quickly. So the bottom, when we revolve this bottom rectangle, it's just one rectangle, really. We could think of it as one big block about the y-axis. We get a single solid cylinder. In fact, we don't even really have to integrate, right? So just using geometry, the bottom is a cylinder of radius 1, right? The length of the horizontal length is 1, and of height 1, because this point here is 0, 1. Cylinder, radius equals 1, height equals 1, and that volume, pi 1 squared times 1, is just pi. So the bottom volume is pi. Now you could still set that up as an integral. You could say that the bottom, the radius is always 1, is the constant function 1, and you'll integrate 1 from 0 to 1 with respect to y. And then you throw in, of course, the factor of pi that you need. So it'll work out either way. But it's sort of easiest to just sort of think of that as a single cylinder. Now for the top, when we revolve this rectangle about the y-axis, we're going to get a washer, because there's a hole. It's not a solid disk. So the width is a delta y width. The length here is, let's see, big R squared minus little r squared. The big radius is from the axis out to the furthest endpoint, so that's constant, that's 1. And the little radius is from the axis out to the curve, so that distance, right minus left, is x squared plus 1. So r squared minus little r squared. Oh, you know what? I labeled that kind of erroneously, right? The length of the rectangle, first of all, we don't need the length of the rectangle. Second of all, the length of the rectangle itself is not big R squared minus little r squared. So what we're going to do, though, is set up the volume of the sample washer, pi times big R squared minus little r squared delta y. And that is pi times big R squared is 1 squared minus x squared plus 1 squared delta y. We can, oh, hold on. I'm going to stop for a second, see if you can't pick out the error I just made. We are integrating, this is a delta y. We're going to be integrating with respect to y. And so this little r value is an x coordinate that we need to get in terms of y. So that's going to change this up a little bit. So they gave us this function, y is a function of x. Since we're going to have a dy integral, we need to get x as a function of y. So x squared is y minus 1. X is the square root of y minus 1. We only need the positive root because this region is in the first quadrant. So little r is the square root of y minus 1. And we're going to put that into the little r squared here. So the square root of y minus 1 squared. That's better. The value of big R is not changed because that length, that horizontal length, is 1. So we get 1 minus, if we square the square root, here we just get y minus 1. Be careful with your signs because we still have to subtract the whole thing. And so this is pi times 2 minus y delta y. So there's the volume of our sample washer for the top. So I'll call that T, V, delta VT. That means that the volume of the top part is pi times the integral of 2 minus y dy, and our limits are going to come from the y limits of this part of the region. So they're going to start at y equals 1, right? So it's that y right there at y equals 1, and then it's going to, the upper limit is going to be where that parabola intersects the line x equals 1. And if x is equal to 1, then this function at y equals x squared plus 1 is equal to 2. So we're integrating from 1 to 2. Now we're almost done. We're going to integrate this with respect to y. We get 2y minus 1/2 y squared from 1 to 2. And now we'll just throw in our limits. Alright, so if you evaluate these expressions, sort of simplifying the numerical expressions, we get, let's see, this first one is 2 minus, this is 2 minus 1/2 is 3/2. And so we've got pi over 2. So that's the volume of the top part. The last thing to do for this problem is kind of put these together, right? We have the bottom and the top. So the total volume is pi plus pi over 2, and that is 3 pi over 2.